Okay, this is part 2 of the 2000 HSC question, question 5. So we're up to part 2. Now we've just proven that angle PBA equals angle PCB. We now have to deduce that PB squared equals PA times PC. Now we know that now PB squared is not a tangent. So you can't use the product of, that the square of the tangent equals the product of the intercepts of the secant. So we're really, I think, going to have to use similar triangles to do this. So often when you see something like that, which is really made up of 4 pieces of information, PB is twice, PB squared is PB times PB equals PA times PC, that must arise from similar triangles. So look, if we look at the 2 triangles that we've got here, I'm going to draw them separately, I think, just for now. I'm going to do PBC, I think, because, yes, you know why? Because we need the length PC and we need the length PA and PB. So I'm going to do triangles, I know, I just hope it works. I'm going to do triangles PBA and I'm also going to do triangles PBC. Now, I've drawn them separately. In those 2 triangles, I know that this angle here is X and I know that this angle here is X. And isn't angle P common in both triangles? So I've got that they're equiangular. Okay? So I'm going to go in triangle PBA. So I need to make some room now. So in triangle PBA and triangle PCB, I've got that angle PBA, that X equals the other X down here, equals angle PCB, and you can just put proven. Oh, was that bit proven? It was proven in part 1 above, and I'm just going to put both are equal to X, all right? It was proven in part 1 above. The other thing is that angle P is common, okay? And so therefore, triangle PBA is similar to triangle PCB. Notice PBA dot cross blank, dot cross blank, dot X blank actually, dot X blank. So they're similar because of equiangular. Now, notice the 2 triangles overlapped and so I drew them separately. It always is a really good idea to do that because if you don't, you could make a mistake and it's just not worth making the mistake, all right? So now that we know that those 2 triangles are similar, we can set up our ratio. So again, we're trying to prove, we're trying to deduce that PB squared is equal to PA times PC, aren't we? Okay, that's what we're trying to deduce. So make sure that when we do our ratios between the triangles that we're using only those sides. I don't want to see a BC in there and I don't want to see a BA in there because they don't appear in what I'm trying to deduce. Okay, so let's do a PB in the first triangle. So PB in the first, oops. PB in the first triangle goes from dot to cross, so it matches with PC in the second triangle. So PB over PC is equal to, now we need a PA, don't we? PA is dot blank, and that matches with which one in the second triangle? With PB. Reason? Yeah. The reason is corresponding sides of similar triangles in the same ratio or in proportion, either. Okay, and now we're just cross multiplying. So therefore PB times PB equals PA times PC. In other words, PB squared is equal to PA times PC. Okay, remember a dot means times. Okay, so girls, the thing is, recognising that this PB squared equals PA times PC comes from a similar triangle proof. And it, 99% of the times it will. Well, it will because we know it's not the product of the secants with the tangent. You can't go and make PB a tangent because it's not a tangent, okay? So that's really the only way that you're going to be able to do it. Okay? Now that's 2000 HSC question 5. I want you now to, you can pause the video. I want you to attempt 1998 HSC question 4. It's on the very last page of your booklet, and then after that we're going to do 1999 HSC question 3. I like these two because they're the tests for cyclic quadrilaterals, or one of them is anyway. Okay? Okay, girls, of course in the exam, you know, I'll try and have a question on each of the types of circle geometry theorems, like there'll be one from the circumference ones, one with a centre one, there'll be ones with tangent ones, there'll be a proof involving a tangent, there'll be a proof involving a cyclic quadrilateral, there'll be a proof for the test of a quadrilateral. I'll try and do one from each category. All right? Chord ones.
Is it going to be one paper on circle geometry and then one on trigonometry?
No, I might just mix it through. I'll just see. I'll just see how it goes. Okay, girls, the first question, we've been given all this information in the diagram. Hopefully you've already read it and attempted it. We have to state a reason why EDCB is a cyclic quadrilateral. Remembering there are 3 tests for cyclic quadrilateral. The first one is opposite angles are supplementary. The second one is exterior angle of cyclic quadrilateral equals interior opposite. And this is obviously the third one, that if an interval BC subtends equal angles on the same side of it, then the endpoints of the interval and the other 2 points are cyclic, or they form those 4 points form a cyclic, other vertices or whatever, the corners of a cyclic quadrilateral. So the reason is for part 1. If an interval BC subtends equal angles on the same side of it, then the endpoints of the interval and the other 2 points are cyclic, or they form, what did it say, girls? Someone got it? I know. How does the end of the theorem go?
If an interval subtends equal angles at 2 points on the same side of it, then the endpoints of the interval and the 2 points are cyclic.
Yeah, are cyclic. In other words, they form a cyclic quadrilateral. I'll just put in brackets. If the points are cyclic, it means when you join those 4 points, they form a cyclic quadrilateral. Okay? So that's the first bit. Now for the second part of the question, for part 2, we need to state a reason why she could then correctly conclude that angle AED is equal to angle ACB. So now, why are we saying that angle, yep.
The exterior angle of the quadrilateral equals the opposite interior angle.
Yeah. So now that you know that those 2 in black are equal, she's saying, well, this red one equals, is that right?
Yeah.
Actually, yes, I think we need to join them. So we need to join them.
That's already joined on the diagram.
Oh, it's joined on the diagram. It was just me that didn't join it. So now, sorry, I'm just knocking everything over. So I want to get rid of that bit. I'll just fix it up. We now know is a cyclic quadrilateral, so therefore we can state any of the conditions of a cyclic quadrilateral. So part 2, so therefore angle AED is equal to angle ACB. Reason, because the exterior angle of a cyclic quadrilateral equals the interior opposite angle. Okay? And that's 1998 HSC question 4. If you could now please try, I'll just leave that there. If you can now try 1999 HSC. Okay, 1999, question 3C. These 2 circles intersect at A and B as shown in the diagram. Okay, the diameter of CA and this line intersects the other circle at A and P, and the line CB intersects the second circle at B and Q. You have to copy it into your booklet, and you have to prove that CPQ is a right angle. Now, this is obviously a straight line. I haven't drawn it very well, all right? So you have to prove that CPQ is a right angle. Be a good idea to join it. So I'd start by saying join PQ, okay? Now you have to prove that this angle up here is a right angle. I would also join AB as well. So we're going to join PQ and we're going to join AB as well. Okay, so I've drawn sort of in red what I've just joined, okay? Now, okay, we know that CA is a diameter, so therefore in the smaller circle, you can call them, you can call the small circle in circle ABC because the small circle passes through the points ABC. So you can say in circle, or the smaller circle, it doesn't matter. But in circle ABC, we know that CA is a diameter, which they told us. Therefore, angle ABC equals 90 degrees. And the reason is that the angle in a semicircle is 90 degrees. So therefore, we know that this angle here, that angle ABC is 90. Now, in the large circle, we know that APQB, so in the larger circle, we know that APQB, we can see that it is a cyclic quadrilateral. And because, so therefore, angle CBA is equal to angle, so remember, the angle CBA, that's a straight line, CBQ. So angle CBA equals angle APQ, or you can call it angle CPQ, because, which is equal to 90 degrees, reason the exterior angle of cyclic quadrilateral equals the interior opposite angle, okay? And therefore you've proven now that angle CPQ is a right angle. Okay, so that was HSC 1999, question 3C. If you could now attempt HSC question 2002, question 2E. 2002, HSC question 2E. Means it shouldn't be too hard if it's question 2E. Okay, first we need to explain why angle ACB equals beta. So part 1, explain why angle ACB equals beta. Hopefully you've already read everything. We know that TA is a tangent, that this TY bisects angle ATB. That's all in that question. Okay, and angle TAB is beta. So this angle here is beta. You have to explain why angle ACB is beta. Girls, angle between a tangent and a chord equals the angle in the alternate segment, my favourite. So let's go. So angle TAB, is that right? Equals angle ACB equals beta. Reason, the angle between the tangent AT and chord AB equals the angle in the alternate segment. Now, for the next part of the question, 2 marks, hence prove that triangle AXY is isosceles. Now, girls, if you have to prove that AXY is isosceles, there are no side lengths. Forget side lengths. You're going to need 2 equal angles somewhere. So we don't seem to really have much here. X is the vertex in the corner. It's not the size of the angle. But what we can do is try and work out either that angle up there, this one here or there. There are no angles in the triangles. You can try for exterior angle of triangles. So that angle marked in red, this one here, is alpha plus beta because it's the exterior angle of triangle TAX. Can you see that?
Yeah.
And also, so we really need another alpha plus beta somewhere. So let's see if we can find another exterior angle. Well, this angle here, angle AYT, is the exterior angle of triangle TYC. So when you talk about exterior angle now, you can't just say exterior angle of triangle. You need to say what triangles we're talking about. So that's also alpha plus beta. So let's start part 2. So we've got part 2, that angle AXY equals alpha plus beta, reason. Exterior angle of triangle, now it's the exterior angle of triangle TAX because we've extended one of the sides of TAX. Exterior angle of triangle TAX equals the sum of the two interior opposite angles. Girls, notice I'm not abbreviating anything except for angle, triangle, equals. I don't want int angles, I want interior. I don't want op, I want opposite. So the only abbreviations that you are allowed is triangle, angle, equals, parallel if it was there, stuff like that, okay? Keep going. Again, angle AYX is also equal to alpha plus beta. You can go similarly for triangle TYC. Do you know what I mean? So similarly, in other words, it's the same reason for triangle TYC.
We don't have to re-say
I don't think you need to because it's similarly the exterior.
we don't need to say TAB equals beta.
Oh, yeah, actually you could say angle AYX is equal to angle, I'd go equals angle TYC plus angle YCT, which equals alpha plus beta. And similarly up here, rather than saying alpha plus beta because it's a bit ambiguous, I could say before that alpha and beta, I should say that angle AXY is equal to angle ATX plus angle TAX, and then go back up to say which is alpha plus beta. Do you know what I'm saying? Got the idea? All right, so the reason we do that, well, you should state them. Look, it'll probably be okay. It's that there are more than one alpha and beta there, and there could be ambiguity in what you're saying. So if there's more than one alpha and beta, you should identify them by doing angle AXY equals angle ATX plus angle TAX, which is alpha plus beta. Exterior angle of triangle TAX equals sum of two interior opposite angles. And in here, don't put this alpha plus beta first. Put that it's YTC plus angle YCT, which is alpha plus beta. Oopsie, bit messy. And again, similarly, the same reason. So therefore, we can say that angle AXY is equal to angle AYX, which equals alpha plus beta. Therefore, triangle AXY is isosceles. Base angles, or two equal angles is fine. Base angles equal. Okay? That's 2002 HSC question 2E. If you could now attempt the next question, which is HSC 2003. Okay. Okay, so homework, can you please attempt questions, HSC questions 2003, 4 and 5. I will do a video on those 3 questions for you. It's actually 4 questions because there's 2003, 4 and 5. And you can keep going a little bit if you want. I'll also send solutions from 2006 to 2013. Okay?